There we go. Right, that's going to be laggy as all hell, but oh well. Yeah, so welcome to the Applied Maths lecture series. Right, is that safe from my head? Yes. Perfect. Yeah, so as I say, we're going to be going in the chapter 1, I guess, but like the first series. One is going to be mechanics. So I think this is a really nice point to kind of start in with, mostly because I think a lot of applied maths tends to start with calculus, and that can be quite far away from like real physical things, whereas mechanics in maths content at the very least, or in maths classes, tends to be a lot more like physical. It broaches physics a little bit more, it broaches engineering a little bit more. Typically this is the bit where people are like, oh, I like this, I don't like maths, and then they run away. So my goal is to like sneak enough maths back into it to show you that you do like maths. But yeah, so we're going to do a series on mechanics problems, and I think it's going to take about 11 streams is how I have it planned in my head. So this is 1, 0, just because it's a bit of an introductory one, so there's a lot of like, I just think it'd be cool to kind of chat about the units and the language of mechanics, basically. So if at any point my handwriting is disgusting because it's been a while since I've used it, please do shout and I'll focus on changing it. But so there's going to be a lot of terminology that we use throughout the mechanics series, and if you are far away from yeah, so there's a load of terminology that's used in applied maths, and it's going to get to the point probably later down the line in a later stream where I say something and I will forget to do a little addendum defining it. So if I do that, I'm sorry. Again, feel free to drop it in chat and I will happily just go over things. The two that I'm gonna like drop to initially are so scalars and vectors, because they're kind of the building blocks of everything that we do. So specifically looking at so like quantities. Scalars. Ooh. Yeah, so whenever I'm talking about mechanics is obviously a study, as someone said in chat, the real world. We're always talking about measuring stuff. And that stuff, those quantities, are either going to be scalars or vectors. So a scalar quantity is an intrinsic thing. It's a value. So it's a value. It's like an amount of something. The technical language says that it's a magnitude or size. Okay, so that's typically going to be broke my own screen. Yeah, so these are just specific values, and without thinking too heavily about it, most things that you possibly think about are going to be scalars. The classic examples, yeah, that does still work as a thing, are going to be things like speed, distance, mass, time, right? They're all numbers, essentially, or they're all an amount. There's nothing more complicated about them. And you might be thinking, like, Kat, that you're just talking absolute nonsense. Typically, this makes more sense in relation to, in contrast to a vector. So a vector then is something that has both a size and a direction. So magnitude and direction. So this is where things like, in contrast to speed, we have velocity. Right? If I'm traveling down a road at 30 miles an hour, my speed will always be 30 miles an hour, but my velocity might be 30 miles an hour west or 30 miles an hour in the positive x direction to make it a little bit more mathematical. And a lot of scalar quantities, not all of them, a lot of spatial scalar quantities do have vector counterparts. Annoyingly, acceleration is the word that we use for both scalar acceleration and vector acceleration. Typically, it means vector acceleration because we talk about acceleration downwards or forwards, and it has orientation. But technically, should be saying like the magnitude or the size of the acceleration to be the scalar one. But if you're just talking about scalar values, not going to be too fussy. The contrast to distance is displacement, right? Because you're displaced in that you're moved away from a reference point. A distance is a distance no matter which way round, where it is in space. A displacement, I'm talking about how far away I am from a certain point in time. Is a complex number a vector? No, but you can have complex vectors. So I can have a vector that talks about, that has complex entries, basically. So other examples of vectors that you might see are things like forces, because you're always acting on something. So essentially think about things that have direction. Similarly, momentum. The example that we've seen from so I used to teach an applied maths course at Bath Uni, and the example sheet the lecturer always used, like the weather is technically a vector because you describe it using vectors and it has direction and it has size. So you could measure it as a vector, which starts getting really like head spinny, but is a cool, like very far steps away from where we are right now. But for the minute, these sorts of things, velocity, displacement, forces, momentum, those are the sorts of things where they've got a size and they've got a direction. Loads of quantities, they all have things, they all have different names, they all measure different things. And the values that they're measuring are sort of intrinsic properties that we use to describe the world. But in order to kind of give them an amount, you kind of need a unit attached to them, okay? So, for example, if I'm talking about distance, if I tell you that the shop is 5 away from your house, for some reason, you're like, how far away is the closest shop? And I'm like, 5. That's not helpful at all, because I haven't given you any units. I haven't given you any sort of relative scale to think about things with. If it was 5 minutes, I could mean 5 minutes walking. I could mean 5 minutes driving. If I said 5 meters, that's really close by. That's lush. If it's 5 miles, you don't want to walk that. So attaching units not only tells you what sort of value specifically you're talking about, but also gives you the sort of relative scale. And as I said, you've got minutes and hours. They're all, different sizes of that value as well. So it's really good and important to check your units. My teacher would always say 5 bananas if we didn't use a unit. Yeah, exactly. The goal is to be as sarcastic as humanly possible until people's, like, the units are embedded in people's brains. So when considering quantities, important units. So it's important to use units to give a sense of scale and determine what it is about, basically. If I do just like tail off and don't explain something, do just shout at me. Different units as well, you might see the argument of so different systems include imperial, metric, SI, to name a few. Arguably, metric and SI are very similar, but they are technically different, I think. I don't actually know. Oh, yeah, they are. They are. So yeah, you might have seen the argument of imperial versus metric, depending on where you are in the world. The main one being like whether you drive in kilometers an hour or miles an hour, measure your height in feet and inches or in centimeters, measure your weight in stones or kilograms. So those are all different systems, right? Because within a system of units, they relate to each other. And you can think of it as so stones have a set number of pounds in a stone and a set number of stones in a ton. Don't actually know what the one up from stone is. Heavier thing. Whereas like inches, yards, and foot, or you go down the metric route and it's all very nicely standardized into base 10. So you have your meter, you have your centimeter, you have your millimeter, you have your kilometer, so on and so forth. And the SI units are the scientific, oh, I should have written this down, scientific index unit. This is why a laptop. International System of Units. Which is arguably IS, but you know, whatever. But these are basically the units that are sort of agreed upon in the scientific community. They're also just kind of standardized. Oh, it's the modern form of the metric system. So the modern metric. And there are sort of base SI units, and then there are derived units in SI. So how much space do I have on this page? Very much. So base SI units. And especially with mechanics, we're going to be talking about things moving and things colliding and things impacting. And we're going to need to talk about time and space and distance and speeds. So having a really good understanding of these units, how they relate to each other, is going to be really helpful. But your base 7, 6. I thought it was 7. 1, 2, 3, 5, 6, 7. Oh, I missed out mole. Whoops. Sorry. So for context, all of the notes from this lecture series, maybe I'll make these available. I did them on my Remarkable earlier and they're all nice and pretty. So this is what I'm working off. So yeah, we have our base units. So they are a value, then the unit, so the name, and then also the symbol. So typically I'm going to jump straight into talking about symbols of things. I'll give you an example to start and we'll go from there. Pre-linear algebra definition of vectors, work with vector space axioms, algebra. Huh. Yeah then. yeah, we're staying away from anything overly complicated with regards to defining definitions for the minute. For the minute. Maybe we'll go complicated later. Anyway, an example of this would be like measuring of length, a value of length, a distance, whatever you want to call it, length, base. The base SI unit of that is meter, and its symbol is M. So 20 meters, 20 M. And this is where, again, the thing, kilometers or centimeters, going up and down the times 10 to the minus whatever, is going to come in helpful. Then we have mass, so a specific amount of stuff. Kilogram. Time is the second. Current. Some of these more applicable to the maths course, some of them more applicable to a physics degree, but we'll put them all down for completeness. Temperature actually uses the Kelvin, which I think I knew that, but I did forget about it. Why is the kilogram a base unit rather than a gram? Really good question. It makes everything nicer, is probably the real answer. So I think this is why the SI units are the new metric system, rather than just being like pure metric, because in pure metric it would be a gram, whereas this is full. As we will see later, once I finish writing this out. I think it's luminosity. Right? Luminous intensity. Luminosity is fine. Basically how bright something is. That's the candela. Different to... The definition of a gram is derived from the definition of a kilogram. Really? So we... okay. Meters of centimeters and seconds over milliseconds. Definition of a kilogram is based on the amount of atoms of something. Oh, is it carbon 12? I thought that was the mole, which is actually the next one. Sorry, amount of stuff. This one's actually amount of stuff. That should be 7. 1, 2, 3, 4, 5, 6, 7. Yes. That's gram based on mole of carbon 12. See, that doesn't feel very, these are the base ones, if you can get kilogram and mole from each other. But I suppose you have to kind of go into chemistry on that front. Which we're not doing. So basically for the mechanics course that we're doing, we're going to be looking at sort of these three basically exclusively. We might do some temperature stuff when considering like decay. Maybe. But generally speaking, length, mass, time are going to be the most important. Current as well, actually, a little bit when we start talking about work and energy. But mostly these. And specifically, this is like electric current. Yeah, moles, again, very chemistry focused, very far away from what I'm doing at the minute. What I at some point found time bit surprising. Some things we consider fundamental maths are actually conventions rather than things that can be derived. Yep. And depending what sort of area of maths you sit in, things that are taken as like truth are very different, which is a lot of fun to cause chaos with. So obviously there's some stuff missing from this list. I even said sort of on the previous page, you know, we talked a lot about speed and velocity, and speed isn't on this list. And that is because speed is actually a derived unit, or has a derived unit. So in contrast, derived units I made combination base units above. So the ones in particular, yeah, you're getting ahead of me. Have you read my notes? So in particular, the ones that we're going to be looking at, again, value. Symbol are things like speed. I think we just say it out, but it's meters. Oh, fine. I'll write it out. I'll write it out. But it's meters per second. Acceleration is per second squared. ms minus 2. And here I'm using the notation I like doing to the -1 rather than over, just because it starts getting very complicated when we start doing dimensional analysis, which, sneaky surprise, we're going to be doing in a minute. So this is the same as meters over second squared. I had to learn this 3 times. Oh, the weights. The International Committee for Weights and Measures approved originally kilogram by defining the Planck's constant in terms of the second and it all sounds very self-referential, to be honest. So glad that we start from lecture 0, not lecture 1. Lol. So the other ones that we have that we're going to be using a lot of are the force, which has the Newton, which has a symbol N. Work, which is done in joules, has symbol J. And power, done in watts, and symbol W. Now, obviously, I can't get an N from, yeah, we can't derive N, J, or W from anything above. Those are new. They do have SI equivalences, but for just completeness, we write a Newton as N because writing it in its full form is complicated. So how do we go about getting it? Well, one way of... No, I'm at the bottom of a page again. So one way of obtaining derived units... Dimensional analysis. I've done that thing where I've written at the top of the page where my head is again. So one way of deriving units is through the dimensional analysis of known relationships. Okay, and the reverse is true as well. If you know all of the units, you can figure out what the relationship between those things is. So, e.g., if speed measured in meters per second, then speed equals is length, distance. God damn it. There we go. So if speed is measured in meters per second, then speed is distance over time, and that's where you get that this triangle from, where you have that relationship between the 3 things. So again, if you have a distance and you do speed times time, you go meters per second times seconds, and they cancel out, and you get meters. So in the same way that works, go the other way. So we know, spoilers, we'll know next stream, F equals ma, okay? Which is Newton's second law, which is force is mass times acceleration. And we know that force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. So that means that we have that 1 Newton is equal to kilogram meter second squared. Now, obviously, that's not how we determined what 1 Newton was, I don't think. Didn't actually go do my history lesson, probably should have. But for us now needing to navigate it, if you have a unit that you don't know if you have a quantity that you don't know the units of, or you don't know the SI units of, this is a really useful way to do about it. And what I just did, this is called dimensional analysis. So this analysis. So it's essentially looking at both sides of an equation or a relationship, looking at a relationship between different known quantities and checking that the base quantities are the same on both sides. Okay, if a Newton was actually equal to kilogram meters per second cubed, then F would be ma over T. Okay. So the units on both sides have to equal. So I was just talking about dimensional analysis. Because they are? According to, at the very least, the Googling and resources I found, the electric current ampere is a base unit. Okay, so dimensional analysis. This is essentially the act of checking, essentially, the base quantity does not start with a D. Base quantity of relationship behave physically. And balance mathematically. No. There we go. Forms the unit charge, ampere is joules per second, if I remember correctly. But you could also say that the joule is joules per second, then a joule is an ampere second. So in the same way, up here, if I had, instead of speed being measured in meters per second, I measured it in S's, then I could have, no, S is time. God damn it. Gammas. I'd have this relationship, right? Where I could say that the M is a gamma S, I could say a gamma is an MS minus 1, and I could say an S is an M gamma minus 1. All of those relationships are true. So even though joule is like one word and a J, that's a derived unit because SI decided, basically. There's probably some nice complicated reason for it, but that's what they've gone with. So when I say balance mathematically, I mean if we have a quantity on one side, we need the quantity on the other. You can't have time equals distance. Okay? Doesn't balance mathematically. It doesn't make sense. Can't have seconds equal. That's both unphysical and bad maths. So whatever values, whatever units we have on one side of an equation, we need the same units on the other, which is how the relationship above, the Newton kilogram meters per second squared. Oh, that's hard to say. This is why they made the word Newton. Because saying kilogram meters per second squared is a mouthful and no one wants to do it. Yeah, it's incredibly helpful. And especially as equations get more complicated than F equals ma, it's something that, you know, I still do very regularly. As soon as you give me a big complicated fluids problem, I'm checking all of my units. I'm doing the dimensional analysis on it. And I'm not preaching. That's genuinely true. I do a lot of what's called non-dimensionalization, which is essentially figuring out what all my base units are and then seeing if I can cancel them out, which is slightly convoluted and way more complicated than it needs to be for this lesson. But fun fact. Thank you so much for the follow. Welcome in. But yeah, so those are our base units. Typically now when I'm talking about things, they're going to have those units. They typically relate to scalars. So as I said, like speed has that relationship. Velocity is also measured in that, but it has that direction as well. So these measure the sort of magnitude of the quantities. Yeah, so we said, so just going back to we'll refer scalar values magnitude of factors. So for example, again, I have two cars that I'm going to draw as circles because I can, and this is going 30 meters per second in that direction, and that's going 30 meters per second that direction. Let's call that one A and that one B. Then the speed of A equal the speed of B. Okay, but if I introduce some directional, so as I said, when we talk about displacement, when we talk about velocity, we do sort of need a reference frame, because we know that those two are going in opposite directions, but we don't necessarily know which one's going in a positive direction or how to describe it. But they're moving opposite directions. So their velocities are different. If x positive increase, right? So I'm now going to define sort of this way as the positive direction. Then as positive velocity and A as negative velocity. I'm going to probably use that notation quite a lot, the sort of like plus V. And I need a third color. What's a good third color? Orange. Shorthand. just because I'm probably going to do it a lot, I'm just going to put that in there. Yeah, so they have, one has positive velocity, one has negative velocity, because we've defined a direction, right? We've defined an orientation. So we've said X positive moves in the X direction. I have no idea if the way that my hand is moving matches with the screen. It doesn't, because there's lag. So that way is positive. But yeah, as soon as we introduce sort of a reference frame, they're no longer sort of aimless in space, and now they're going definitely in opposite directions. So that side note. And so when we define directions or orientations for vectors, typically one of two coordinate systems. Now, there are a lot of coordinate systems, and there are a lot of right or wrong or questionable answers in between. We're going to focus on the ones that are needed for the sorts of questions and problems that I'm going to ask. I am aware there are others, and I am aware there are generalizations, but for the minute, we're just going to stick with those two. Yeah, okay. So our two coordinate systems, the sort of most common one, which people probably will have seen whether or not they know the name for or not, is the Cartesian, which if we have our grid like this, we have our X and our Y direction, we call them the X-axis and Y-axis, and if we were in three dimensions, we would have, how is my 3D drawing? This. And obviously there are negative space as well. Like I could have drawn this like this and then have more around it, but for space I'm just doing positive area for the minute. Same with this. This makes a big cross in space. We put our origin where they intersect, so that's a 0 at that point. And we describe a point in the plane space. So over here we have a point xy. So, and then over here we have xyz. And vectors can also be written vertically if you want, if you're feeling snazzy. Like that. Doesn't matter too much right now. Don't worry about it. But for the moment, it's just sort of your preferred notation. X, Y, Z might differ depending on person. Some people use Y for up, others Z for up. Yeah, depends entirely what you're doing. If we have a point in space here, call it P. Those two values correspond to X is sort of the distance along here. So this length, X. And this distance, little Y primes. X prime, Y prime, X prime, Y prime, just to distinguish them from the X and Y axes. So it's essentially your distance horizontally and your distance vertically. So distance along axis. And I lied to you because we also have a secret third way of writing it, which we will need later on, which is X dash I plus Y dash J. That is possibly the worst J that I've ever done, ever. There we go. Now these J's, I's and J's, correspond to unit vectors. So So I, J, K in the Z direction are unit, and unit here means length 1. I can spell length 1 vectors pointing X, Y, Z directions. Okay, so if I were to draw it out in full, you have your axes which go on plus and minus infinity in each direction, Z, Y, X. And then you have tiny little vectors of length 1. So I, okay. And you could think of, if I wanted to write them out in those things, this would be 1, 0, 0. J would be 0, 1, 0. And K would be 0, 1. Because there's nothing, if I want to go I go 1, unit 1 in the X direction. I don't go in the Y, and I don't go in Z. Same with J in the Y, same with K in the Z. So yeah, that's how we describe vectors in space. And again, they can correspond to different scalar quantities, but just so when we go down the line, I start talking about things in the positive X direction, I mean, inline, it's probably going to have a value of like 3i, for example. Quickly, we're going to do the other one. Polar coordinates. So these won't come into play for a while, but if I didn't mention them now, it would upset me. So we still make our space into a grid with our X and Y axis and our 0 in the center. But now, if I want to describe a point, and I'm just going to do this in 2D, don't worry about cylindrical or spherical polar coordinates, that's not relevant right now. So if we do a point P, instead of going along the x-axis and up the y-axis, we do a straight line from 0 to it. And actually, I think I can do that better. There we go. And let's make that point bigger. Okay. So we draw a straight line and we say that distance, so it's the shortest path traveled, that direct distance has a value of r. And then we look at, from that line, from the positive x-axis round. So starting on the positive x-axis round, and we look at that angle, and we call that angle theta. So now we say that P as a point has coordinates r theta, where r is distance from origin, and theta is angle from positive x. Okay, so instead of now our vectors that describe it, it's not nice like IJK. They're a little bit more complicated, so we're not going to worry about them so far. But what I am going to do is write the polar coordinates as the IJK. So here is r cos theta I plus r sine theta j. Have I got that the right way around? Because I always get it wrong. Yes, excellent, go me. So here, cos and sine are your trig functions, r is your radius, your distance away, and theta is your angle. So a little bit more disgusting, but generally we're not going to worry too much about that. We're only really going to worry about polar coordinates when we start looking at things moving in circles, or we start looking at paths along a circle. So for most of the time, we don't need to worry. We're going to be working in this coordinate system in Cartesian, and it's going to be absolutely lush. It's all going to be fine. But it is really important to have kind of a good grasp on this, because it is going to start getting quite quickly derailed. So yeah, that's our quick quick lesson on coordinate systems. Yeah. So the only other thing that I want to do for the rest of this stream, and we've got a 1 minute time. Anyway, we're going to jump to a quick ad, but the last thing I want to go over is keywords and terminology. In questions, especially during like exam style questions, so the entrance exams, A levels, whatever, they tend to like throwing really weirdy problems at you. Because if I draw you a diagram, a lot of people are going to find that really, really helpful. So instead of giving you that answer, what they tend to like doing is giving you a description and a diagram, or just giving you a description and making you do the diagram yourself. There are a few like keywords that are going to pop up a lot that are sort of well known, and these are definitions in exam settings most of the time. Some of them are just true. Okay, so you've got things like these words, definitions are specifically referring to their use exam style questions. Okay. And that's things like light, meaning that something has no mass. Okay, so if they talk about like a light string, for example, they're like, disregard the mass of the string. The mass of the string is negligible. Don't worry about it. Other ones that also mean none of that, thank you, are smooth, which means no friction. So a smooth surface will be like perfectly smooth. There's no friction. You don't need to worry about that at all. A light and extensible string. Yeah, anyone that's just got like trauma flashbacks from exams is gonna get that again. So inextensible means no stretch. Okay, there's no elasticity in it. It doesn't stretch. It doesn't extend. Yeah. The other one is no, technically, is particle, which is no dimension. Or no size, really. Yeah, I'm going to put no size. So rather than modeling like a ball or a person, right? People have limbs, our mass is distributed unevenly throughout all of us. That's really annoying. So instead what we do is we say that they're a dot. They have no size. They are just a particle, a single like point in space. On that note then, you've got things like uniform, which does what it says on the tin. It doesn't wear a snazzy outfit. It's even distributed. So a uniform weight. If something has uniform weight, it means throughout its entire body. If it's not a particle, the mass is the same along it, or the value I'm talking about is the same along it. If I talk about cars moving with uniform velocity, they're all moving at exactly the same velocity. So on that route, you might see a uniform rod or beam, which is essentially like a long particle. So it's like, what if no size, but one size? So instead of being like a dot, a rod is, you model it as just a line. And it might be a uniform rod. So a uniform rigid. If it's inextensible, it's got no stretch. If it's rigid, it's got no bend. So exam question might be, I'm trying to hang a painting from a point on the wall, model the painting as a uniform rigid rod, of mass 20 kilos, where do I put the pins on the wall, as an example, so that it balances. And smooth, we've done uniform, rigid, light, inextensible rod, particle. The other one that only really appears in exam papers, as far as I can tell, is the word laminar, which there's laminar flow in fluid dynamics, which if you've watched my video that I did with Simon ranking fluid phenomena, I put above turbulence. You have turbulent flow and you have laminar flow. But I believe that one's spelt differently. Or am I? Yeah, laminar. So laminar flow, which is the same spelling with an R on the end, means everything's gliding over each other really smoothly. Laminar, in this sort of context, is what if 2 dimensions? So it's a like very thin plate. Thin plate. So it's like the thickness, negligible, of. So at this point, you sort of have, I'm so annoyed I have to go onto another page. You have like particle plus dimension, like a rod. It doesn't have to be a square. It can be any shape. Laminar. So essentially, yeah, you start from, these are your sort of like basic things. We never really model things in 3D because it starts getting really complicated. But you can think of this as like 0 dimensions, 1-dimensional, 2-dimensional shapes. Okay, so yeah, this is a nice thing of if you see an exam question or you have a problem, you can model things as a particle if they are just a point, a rod or a beam in 1D, a laminar in 2D. If it's 3D, you're on your own. That's outside of our remit for today. And then the final ones, assume. We tend to always assume, unless stated otherwise. Because you've always got to have a caveat that gravity uniform, constant, and vertical. But it can move up or down, so you know it's not always downwards, just to make it snazzy. And air resistance. Negligible. Again, unless stated otherwise. So unless you're looking at a problem that has drag or air resistance in it, yeah, it's basically not there. As a cheeky little recap, what have we done today? So we started the Applied Maths lecture series with the first of the mini-series in mechanics. Specifically today then, we looked at the units, language, and quantities of mechanics, so the sort of building up the basics of the next few streams in this series. We talked about scalars and vectors. So scalars being just values, sizes, magnitudes of stuff, whereas a vector then has the magnitude and direction of it. We talked about different units, had a nice little rant about imperial versus metric and how everything's broken, and then went on to the System International of units, the SI units that everyone tends to agree to use politely, unless you're America for some reason, but who knows. We looked at what the base units are, so the core units that we use there, these to build up other units and other measurements. Specifically, we're going to look at meters, kilograms, seconds, maybe amperes down the line, but meters, kilograms, and seconds are our friends. The others scare me. Derived units then are combinations of those, for example, speed being meters per second. And that's what makes up the relationship between velocity, time, speed, time, and distance, because the unit of speed is a relationship between distance and time. That led on to a conversation about dimensional analysis and how if you know the relationship, you can get the units, and if you know the units, you can get the relationship, and how it's really important that check your system is physical in that the units are correct on both sides of your mathematical equation describing the system, or that you haven't accidentally said that like time is equal to a distance or something crazy like that. This is where like light years wind me up, but you know, whatever. We had another little backtrack onto vectors, and now we know how to describe their units. We also know how to describe their directions, and to do that we need a coordinate system. So we had a nice little segue onto learning coordinate systems, where we talked about Cartesian in 2 and 3 dimensions, where we describe things with x, y, and z, or I, j, k being those unit vectors, so vectors of length 1 just pointing in the specific directions. And then we also looked at polar coordinates, where instead of sort of moving along the axis, we go straight to the point and an angle around from the origin. And that's our polar coordinate system. We're not going to worry about that right now. Finally, we defined a load of words, and basically realizing at this point that maths, applied maths, mechanics, most things that we do are sort of, what if we have a real system and we just chuck out a load of stuff? So we learned the standard terminology for getting rid of the mass of something, getting rid of the friction, getting rid of the air resistance, reducing the dimension, and just making it a bit easier to actually do some problems with. And yeah, that's basically it. That's what we've done today.